Get this show on the road. Hello, everyone. Hope you're well. Welcome to another lecture of Math 391 differential equations, mostly ordinary differential equations. Very important lesson today. We are going to deal with second order linear differential equations. Well, a very special version. And then we'll talk about some more general things that have to do with nth order linear differential equations, kind of a teaser for some of the theoretical things that we're going to be going through in the future. It's going to be very exciting. And it's also surprisingly useful when it comes to applications. If you're thinking of like engineering specifically, it turns out that if you know about second order differential equations, you know a lot. By far, most of the applications in the real world will be applied to second order differential equations. There are a few people who might need to know higher orders than that, and we will cover higher orders as well. So I can think of maybe a couple instances in like fluid dynamics, like if you're an engineer studying fluid flow or something like that, you might need a seventh order differential equation or something. But by far, most people will never need to actually know anything beyond second order. So it's actually a very important topic to cover. We're going to cover it. I'm going to talk about the basics of how to do computations, how to actually solve one. Then we're going to look at some theoretical underpinnings. And then starting next week, we're going to solve slightly more general and general cases. And eventually we're going to do some applications. So that's what we're doing. And let me just share the OneNote document. So there we go. And let's turn off the videos so we can get rolling. So remember, a long time ago, we defined what the order of a differential equation is. The order just is the highest derivative that visually appears in the equation. So of course, a second order differential equation just refers to a differential equation where there is a second derivative present. So just a second order ODE in general is just some equation that we can write in this form. It has a y double prime, and you can think of it as a function of an independent variable t, as well as of a dependent variable y, as well as potentially the first derivative of y as well, but definitely there's a second derivative present. That is just the general definition of a second order ODE. That's what we have. That's what we have right here. However, we are going to actually break that down a little bit before we can get to attacking second order ODEs in more generality. We're not even going to go the most general that we can get in this class, but we're going to do a little bit more general than we're going to do today. We are going to talk about specifically linear second order ODEs. So second order linear ODEs, I'm going to call these guys SOLDE for short, at least typing them. Normally when I'm saying it, I'll usually say out the entire phrase, second order linear ODEs. But if you're typing or writing down SOLDE is understood. So this is pretty much when your f that is described above is a linear function. Specifically what that would mean if I had to write this out, it is a differential equation in which the standard form, remember standard form just means that there's a 1 as the coefficient of the highest derivative. You can divide through by the coefficient of the highest derivative. And the standard form of a second order linear ODE is y double prime plus some function of t times y prime plus some function of t times y equals some other function of t. Customarily, we call these p, q, and g respectively. You should also notice that if it's not in standard form, it can look something like this, some function of t, y double prime plus some function of t, y prime plus some function of t, y equals some other function of t. This is p y double prime plus q y prime plus r y equals g of t respectively. And that's, again, pretty common to use those letters, at least in our textbook. They tend to use the p, q, r, and g to represent these guys respectively. So that's more of a slightly more general version, right? So that's the most kind of general version of a second order linear ODE. Now, just to talk about a new phrase, this is important as well because it's actually remarkably different to how we use this word in the past for the first order. So we spoke about first order homogeneous before, and that basically means that we could express it as a function of y over x, which means that if we replace all x's with k times x, replace all y's with k times y, it actually gives us back the original function. However, homogeneous for all other situations means something completely different. So we say that a linear ODE is homogeneous if the g of t is actually equal to 0. So a homogeneous second order, linear second order, would look like y double prime plus p times y prime plus q times y equals 0. So when 0 is specifically the guy that's right here, we call the equation a homogeneous equation. Now, knowing how to solve the homogeneous case is super important. In fact, we need to know how to do that in order to solve the general case. So for a while, we're going to focus on homogeneous differential equations. Also, on top of that, solving it with general functions in the P and Q, that is also in and of itself difficult. What we're going to do is we're going to even break it down further and study a special case of the already special case and study homogeneous second order linear differential equations with constant coefficients. So we're really just backtracking, right? So we start, okay, let's study second order differential equations. All right, that's kind of too hard. Let's study linear second order differential equations. All right, that's still kind of too hard. Let's study homogeneous second order linear differential equations. Yeah, that's still kind of rough. All right, let's pretend that the coefficients are constants. So this is one of the most basic scenarios that you are going to find yourself in. And yes, it is still surprisingly actually quite useful. There are many applications for equations of this form. We'll see some in this class, but this is where we're going to start. We're going to learn the ropes of how to solve these guys using this form. And then we're going to start build up to more general cases in the future. So for a while, we're going to spend time on the homogeneous second order linear differential equations with constant coefficients. Of course, for the y double prime to be present, the a has to be non-zero. So we're looking at guys where that look like a y double prime plus b y prime plus c y equals 0, where the a, b, and c are constants, and the a is not 0. Of course, if your a is 1, it's in standard form, but it might not be given to you in standard form. So this is the guy we're going to really focus on today. This is the main focus for at least the first half of the class. Okay. So right now we're going to be learning how to solve guys like these. So how do we solve homogeneous second order linear differential equations with constant coefficients? And here's what we're going to do. We begin by guessing, right? Now, last class, yesterday, I mentioned that we're going to start doing things that you're probably going to wonder, what do you mean? Is that allowed? Can we actually do that? Well, and is that really going to find everything we need? And the answer was yes. And it's something that I have to explain and justify more fully later. But for now, I'm just going to tell you this is how we're going to do it. We're going to begin by guessing that there's a solution of a certain form. Specifically, we're going to guess that there is a solution to this equation of the form e to the RT, where e is a constant. Now, this might seem like a completely random guess, but it is not completely random. Essentially, look at what needs to happen for this equation to work out. Look at this homogeneous equation right here. If I'm saying a constant times y double prime plus a constant times y prime plus a constant times y all equals 0, essentially what that means is these guys need to essentially cancel each other out. There must be a way for me to add some multiple of y double prime to some multiple of y prime to some multiple of y, and they'll all cancel each other out and give us 0. In other words, these guys need to be like terms because the a, b, and c are constants. They need to be like terms in such a way that they all combine to give us 0. But what would it mean for these functions to be like terms? Well, that would mean that the y and the y prime and the y double prime are all very similar to each other. They're all potentially a constant multiple of each other. And so when you think about, well, what kind of functions do we know about are all just multiples of each other? And the exponential function is one of the first non-trivial functions that you can come up with in saying this, right? So of course, this is true for constants. If you take y equals a constant, then all derivatives are multiples of each other because all derivatives are going to be 0. But if you want a non-zero answer, you want an answer that's a little bit more exotic, the exponential function is actually pretty obvious a choice. Now, I'm going to explain to you later on why we can realize that this will cover all possible scenarios for the solution. But for the moment, just run with me here, and we're just going to guess that we have a solution of this form, y equals e to the RT. Okay, so we're going to start with a guess. That's how it all starts. And we're going to hope that this is going to work out to something that we can actually use because, you know, that's differential equations is about hope. A lot of math is about hope. All right, so here's what that would mean. If I pretend my y is e to the RT, that would mean my y prime is r e to the RT, and my y double prime is r squared e to the RT. And since y equals e to the RT is a solution, it must satisfy the differential equation, which means if I plug that into this equation, I should get 0. So let's actually plug these guys in and see what we get. Right? So I'm going to plug in. I would get a times r squared e to the RT plus b times r e to the RT plus c times e to the RT by replacing my y with e to the RT. So now, I'm going to essentially want to find an r that makes this true. Now here's something we can do. We can actually divide by e to the RT. Since it's non-zero. Right? The exponential function is never 0. That's a fact that we knew a while ago. So we can divide through by e to the RT because it's not 0. And what we're going to get is we're going to get AR squared plus BR plus C equals 0. And so by assuming a solution looks like e to the RT, we end up with this equation right here. Now, of course, it's a quadratic equation. And in theory, we all know how to solve that, right? So this leads to a polynomial. Specifically in this scenario, it leads to a quadratic. For higher orders, it will lead to just some nth degree polynomial. And this is what we call the characteristic equation of the ODE. Now, it's just a polynomial, which means it's just a quadratic, which means we can find the solutions to this based on 3 cases of the solution to this characteristic equation. That's why it's called characteristic. You can describe almost everything about it. And these are the 3 cases right here. Can move this up a little bit. So now you start to think about what would the solutions to this quadratic actually look like? Right? So that's one thing you can start to think about. Well, if I go and I solve this random quadratic, what situations can I find myself in? And you will realize, especially with what I told you about complex numbers yesterday, that there are really only 3 situations that you can find yourself in. One, the quadratic can have 2 different answers for r, right? You can be a quadratic that crosses the x-axis in 2 different places. Or another case, you can have 1 solution, meaning that this quadratic is, you can actually complete the square and it's actually can be written as a complete square, and there's only 1 point. So this is like a quadratic whose vertex touches the x-axis and then it expands away from the x-axis. Or you can have a quadratic that does not touch the x-axis at all, in which case there are no real solutions, but there will be complex solutions. There will be imaginary solutions that we can't really see on the real line, but they exist. And we can write these guys in terms of the imaginary unit I and get a complex solution. So this basically leads us to the following strategy for solving second order linear differential equations with constant coefficients. So right now, I'm going to tell you everything you need to know about how to solve these guys. That's in this table right here, which will be in the notes. So given some second order linear differential equation with constant coefficients, you're going to set up the characteristic equation. Because we know that this is always going to happen, you don't have to write it down every time. You can just go straight from the differential equation to this quadratic. Clearly, you can see that it's like replacing the y double prime with r squared, replace the y prime with r, and replace the y with just 1. So you can literally read the quadratic right off the differential equation. So the first thing you're going to do is you're going to set up this characteristic equation. The second thing you're going to do is you're going to solve the characteristic equation. So this means you're going to like factor and find the answer, or use quadratic formula if it doesn't factor, and potentially you can get imaginary solution, complex solutions here, right? So as I mentioned, there will be 3 cases. You're either going to have 2 distinct real roots. There are going to be 2 numbers r1 and r2 that solve the equation, or there's going to be 1 solution, call it r, that solves the equation, or you're going to have a complex solution, a plus ib solves the equation. Now, in the case that 2 distinct numbers solve the equation, this is going to be the form of your general solution. In fact, maybe I should put general solution. General. So the general solution is that. Here, the general solution is that. And here, the general solution is that. Okay? So remember, we pretended our solution looked like e to the rt. But here, in the first case, we have 2 possible r's, r1 and r2. So we have e to the r1t is 1 possible solution. We also have e to the r2t is another possible solution. And if we combine them in this way, which is called a linear combination, we'll talk about that later, we get another solution. This is in fact the general solution to the ODE. And I'll talk a little bit more about that later. But for now, just know that that's going to be the form of our solution. Secondly, suppose we only have 1 answer. So there's only 1 r that solves this quadratic. Then the general solution will look like this form. E to the rt is going to be 1 solution. It turns out that the second one is going to have the form te to the rt. That is something that we're going to justify when we get to section 3.4. But for now, just take this for granted that if you have 1 solution, you're going to have 1 of the e to the rt. And then for the other guy, you're going to multiply by a t. Okay, so that's the second case, the repeated root case. In the complex case, it's going to break down into exponentials and sines and cosines. And you might wonder, well, why does it look like that form? Well, remember last class, right? Like we didn't do all this work for nothing. There was a reason. Last class, remember, if we plugged in something that looks like a plus ib to the t into an exponential, it breaks down by Euler's equation into something that looks like this. So one of the solutions is going to look like this, e to the at cosine. The other solution is going to look like e to the at sine b t. However, your I is a constant. So if I multiply this by a C1 and that by a C2, I can absorb the I into the C2, and ultimately I can get it to look like this guy right here. So this is going to be the general solution in the complex roots case, okay? So that's basically it. So we are going to do some examples now of solving differential equations in this form. So we have and that for us is going to actually wrap up this section, at least how I'm presenting it. What I just did actually was I presented theorems from section 3.1, 3.2, 3.3, but I think it's just nice to do them all at once and just for you to have a general idea. So again, this is going to be in the PDF notes of the class. However, for the time being, I'd like you guys to actually take a screenshot of this and because I'm actually going to ask you guys to use this fact to help us solve the equations. So I'll give you 5 seconds to take a screenshot or a picture because you're going to be referring to this. Okay, so 5, 4, 3, 2, 1. Okay, great. So we all have a picture of that. These are the cases once we set up this quadratic equation. And I might be able to maybe reduce this a little bit so you can see everything all at once. So that's the whole table all at once, including the steps to solve the equation. So I'll give you 5 seconds to do that. 5, 4, 3, 2, 1. Okay, make this a little bigger. All right, so now those are the steps. Now, the cases that everything like why the solution looks this way and all of that is actually covered by the existence and uniqueness theorem up to the form of the solution. Case 1 follows immediately by our assumption. Case 2 comes from a technique called reduction of order. We'll actually cover that in section 3.4. And case 3 follows by applying Euler's equation, which I just showed you earlier. So now let's actually just do some examples and let's solve these. So let me work through the first one. I am going to actually ask you guys to help me with the second one. So here's my equation. I realize that this is a second order linear differential equation with constant coefficients. How do I go about solving such an equation? Well, the first thing is I would set up the characteristic equation. Right? So in this case, that's going to look like r squared minus 4r plus 3 equals 0. So that is the characteristic equation. And again, it looks just like a quadratic where the y double prime is replaced by the square, the y prime is replaced by the r, and the y is replaced by 1. So that's the characteristic equation. The second thing I'm going to do is I'm going to solve the characteristic equation. And I'm not always going to write out these steps here. You don't have to write these out all the time. So here it looks like these guys should actually factor. It looks like a -3 and a -1. So I would get r equals 1 or r equals 3. Notice here we have two distinct real numbers. This means we're in case 1 above. So what does that mean for the general solution? Well, 3 state general solution. So this means that the general solution is going to look like y equals some constant times e to the first r times t plus some other constant times e to the second r value times t. And that is the general solution for this ODE. There we go. That's the general solution. By the way, in this case, I think I mentioned this in the notes somewhere else, but in this case, the general solution is called the homogeneous solution or the complementary solution, and that's because it solves the homogeneous equation, right? We're going to talk about other kinds of solutions as well. So the general solution here, equals the homogeneous solution. But it may be different in general. And I'll talk about the other cases. And that's that. So I have one, right? It's not a big deal so far, right? With constant coefficients, it's really not a big deal. It comes down to you solving a quadratic. Got the second order linear differential equation with constant coefficients. Jump to the characteristic equation, which you literally write the coefficients of the y double prime, y prime, and the y, and line them up in a quadratic. Solve the quadratic. In this case, I got two distinct real roots. Now I put them in the form e to the rt. So it's c1e to the 1t plus c2e to the 3t. This is my general solution, which is in this case the homogeneous solution. And that's going to be our guy. Any questions on that? There's no catch. When it comes to these equations, that's it. The catch is if we don't make the coefficients constants, then things start getting really hard really fast. But for now, for this section, there's no catch. That is it. So the 1 and the 3 are our R values. We plug that in the e to the rt, and then we combine them. We say we form a linear combination of them, and that's going to be the solution. So when it comes to these guys, there's no catch. The catch comes in when we look at a more complicated type of equation. But for these types, that's all they're going to be. So now you guys are gonna help me with these. All right. So here's a differential equation. Go. Tell me what I need to do. You see that? That shows up on a quiz or a test. What's the first thing you write down? Characteristic equation. What's it going to look like in this case? Right, 2r squared plus 3r minus 2. Yeah, so you're going to say 2r squared plus 3r minus 2 equals 0. Then, how do we solve that? Yeah. All the kids in pre-calc, why do we need to know this? Well, dividing through by 2 will leave me with a 3 over 2 in the middle term, which I think would be more annoying than helpful. So I probably wouldn't divide by 2. Symbol lab? No, not allowed. It's also quadratic. You shouldn't need symbol lab. Well, you always try to factor, right? You always try to factor. So here, you see if there's a 2r and an r that can work. How can you get to 2? Well, you have to get a 2 and a 1. Maybe I put a 2 here and a 1 here. Then if I look at the outer terms, this gives me 4r. The inner terms gives me r. Can I get to a positive 3 using a 4r? Can I get to a positive 3r using a 4r and an r? Well, sure, if I make this plus and that minus. So what I can do is set this is minus here. This is plus here. This is the factored version. This factors, right? You guys have to remember that, how to factor a quadratic. It's not. Now, of course, you could use the quadratic formula, but at some point, it's like factoring is going to be easier to do in your head than the quadratic formula. So that would be that. So our solutions here is r equals 1/2 and r equals minus 2. So what does that mean the general solution looks like? So if you're typing, I guess you can use C and D for the two constants, C1 and C2. What would it look like? Or I guess you can just tell me what it would look like. I don't know. Well, Is anybody out there? C1e to the 1/2 t plus C2e to the minus 2t. Yeah, and that's it. There's no catch. That will solve the equation. And that's it. That's a fully worked out problem here. That's all there is to it. No catch. You write down the characteristic equation. You solve the characteristic equation. In theory, the assumption is every student in this class knows how to solve a quadratic equation. So you're going to solve that. Then you're going to plug in what the answer looks like based on the cases I told you before. And again, here we're still in case 1. So that's that one. Okay, so let's look at another example. Now, this example is something that we've covered before because at least a part of it, the y double prime minus 4y prime plus 3y, this was actually the first example. So we already saw this, so I'm just going to skip ahead. We saw that r equals 1 or r equals 3, so that our y is c1e to the t plus c2e to the 3t. Okay, so we saw that earlier, right? We did that up here, c1e to the t and e to the 3t. So we saw that earlier. Now what happens is that we're given initial conditions. Here, we're given initial conditions. So pretend I gave you the original problem with initial conditions. This means we need to solve for the arbitrary constants. There's a specific one of these functions that is going to give me what I need. Solve for the arbitrary constants. Now notice here, our initial conditions are given, we are given two pieces of information. Insha, you lost connection. I don't, well, yes, your answer was right. The R values were 1/2 and minus 2. It's up here. That's it. So your R was 1/2 and minus 2, and then the general solution would look like that. Okay, so now we are looking at another example, which is the first example, except here I added initial conditions to it. Notice here I have two pieces of information. I know y of 0 and I know y prime of 0, which means I'm in a situation where for this function, I know its current position at a certain time, and I also know its speed at a certain time, which I know, take that Heisenberg uncertainty principle, right? Like, whatever. Let's suppose we can be certain of these two pieces of information, right? We can simultaneously talk about position and velocity, which, you know, for electrons, this is, of course, remarkably difficult. But let's say we are looking at something that we can actually track these things. So you're going to plug it directly into the first condition. That's fine. You have to derive the solution to plug into the second one, as Roberto says. So yeah, that's what we're going to do. So with the initial conditions, in order to plug it into y prime, I'm going to have to actually find y prime. So here, I'm going to find y prime. This is going to be c1e to the t plus 3c2e to the 3t. Then I'm going to plug in the initial conditions. Y of 0 equals minus 1 means that if I plug in 0 for t's in the y equation, I would plug in y equals minus 1. So in other words, that means my which means I have -1 is equal to C1 plus C2. And in the second one, if I have y prime of 0, we were told that that is -7. This means -7 is equal to C1 e to the 0 plus 3C2 e to the 0. So that gives us that -1 minus 7 equals C1 plus 3C2. Now, of course, the lines where you're plugging in e to the 0, you don't have to actually write that down. So you don't need to write. Because you can immediately see that if you plug in the 0 in the power of e, it's just going to become 1. So you can actually just skip to the second line. So you don't need to write this. Okay. So now notice we have 2 equations and 2 unknowns. So here I have my equation 1. Here I have my equation 2. And what I can do is I can just subtract 1. So let's say subtract 1 from the other. Say take equation 2, subtract equation 1. What would I get? Well, I would take -7 minus a -1. That gives me -6. C1 minus C1, the C1's die. 3C2 minus C2 gives me 2C2, which means that my C2 is equal to -3. Then I can plug this in. This means that -1 is equal to C1 plus -3. So in other words, this means that my C1 is going to be 2. Right? And I just plugged it back into equation 1. So this means my y that solves this scenario is going to be 2e to the t minus 3e to the 3t. And this is what we call the particular solution, although we're going to use that phrase to refer to something else as well. And there we go. Any questions on that? The process of finding the arbitrary constants. So here it just means that we had to differentiate the solution, plug in the numbers into the original general solution. We'll get a system of equations. Of course, you can kind of guess that if we had a third order in a similar situation, we would need 3 pieces of initial conditions. Or if we have a fourth order, we would need 4 pieces, because we'd have 4 unknowns to solve for. So we need that many equations. So for a second order, you really need 2 initial conditions to identify the specific function that's going to work in general. Okay, but this concept here of finding the arbitrary constant isn't new. We've seen that before. So let's just move on. All right, let's do these guys. Okay, go. Y double prime plus y equals 0. What is the solution, the general solution? What do I write down first? We're not missing y prime. It doesn't matter. It means that the b is equal to 0. Remember your training, grasshoppers. It does not matter. Write down. Basically, this just means you have y double prime plus 0 y prime plus y equals 0, which means that your a is 1, your b is 0, and your c is 1. It does not matter that any one is 0 except the A. The A definitely cannot be 0, because if your A is 0, there's no y double prime, and you're not a second order. But the other two guys can actually be missing. It's not a problem, right? It just means that their coefficients are actually, sorry, I have to clean my glasses here. There's a smudge. It just means that the coefficients of the others is 0, but it does not change anything. We're just going, as long as the y double prime is present, meaning his coefficient isn't 0, we don't care about any of the others. We're going to just go straight through and write down the characteristic equation. In this case, it's going to be r squared plus 1 equals 0. What is the solution to that? Right. R is now plus or minus I. That is a complex solution, which means we are in case 3. So now you can look at the screenshot that you took and tell me what must the answer look like. What does the general solution look like to this guy? No. I mean, did you guys look at it? Here's what we're looking at. We're in case 3. This case right here. If your R is A plus or minus IB, then the general solution looks like that. So if we know that our R is A is plus or minus I, based on this form, what does that look like? Right, this is just C1 cosine T plus C2 sine T. Notice that note, if you look at plus or minus I, this is just 0 plus or minus 1I. So it looks like A plus or minus IB, where A equals 0, B equals 1. So you just go into this general form that I had here, plug in A equals 0, so you just have e to the 0, so the exponentials disappear, they just become 1, and plug in B equals 1, so I just have cosine of 1t and sine of 1t. So I have this as the general solution. So now that's case 3. And individually, it's easy to see that these guys are going to be solutions, because I mean, think about it. If you differentiate cosine twice, what happens? Differentiate it once, it becomes minus sine. Differentiate it again, it becomes minus cosine. So if I add the y double prime to the y, I get 0, because I would be adding cosine to minus cosine. Similarly for the sine, differentiate it once, you get positive cosine. Differentiate it a second time, you get minus sine. So the y double prime would be minus sine, and the y would be sine. If you add those together, y double prime plus y, you would get 0. Individually, it makes sense that these functions actually solve the differential equation. Why does this combination solve the differential equation? Well, I'm going to actually explain that to you in a little bit later. But yeah, that would be the solution. This is the general solution for this differential equation. Again, go to the characteristic equation, solve that. When it gets complex roots, that means you're in case 3. Apply the formula for case 3, that's your answer. Okay, so that was example D. Let's look at example E. Right, so here, I'll do the first couple steps for you. We're going to notice that this gives us r squared minus 2r plus 1 equals 0. you'll notice that this actually factors, or hopefully you should notice, this factors into r minus 1 all squared. This means r, both versions 1 and 2, is equal to 1. This here is a repeated root. This is what we call a repeated root. It's the same root doubling up. So this means we're actually in case 2. So I have r equals 1. And so this means our solution looks like, here's where you guys chime in. Let's see here. C1e to the t plus C2t to the t. Yes, that's correct, based on case 2. All right, last example in this section, or in this section, the way I'm presenting it. Technically, we covered important data from 3 sections just now. I just went through the 3.1, 3.2, 3.3, and picked out the straightforward computational solution ideas, and I put them all together. All right. So here's what I'm going to do for this one. I will give you guys 3 minutes, solve this, and then tell me what the answer is in the comments, or maybe you can say it. I don't know. Don't use a computer. Don't use Symbolab or Wolfram Alpha. Do it by hand. Get it done. Go. I guess when you find the general solution, you can let me know what it is, and then you can continue on to finding the particular solution. Okay, so I have a guess as to the general solution. All right, go ahead and find the values of C1 and C2 and let me know. I don't know, whatever you think the answer is, just put it in the comments. Yeah, sometimes the computer automatically corrects lowercase I to uppercase I. You can press Control Z. Sometimes if you press backspace, it'll do it as well. A little less than a minute to go. Okay, so we have the final guess. Kevin entered the equations, but I'm not sure what his original guess was. But that's enough times. Let's see what we got here. All right, so I see this. Remember, the first thing we're going to do is we're going to jump into the characteristic equation. We're going to figure out how to solve this. Now, I want to think of two numbers that when I multiply, I get 5. And when I add, I get 4. 5 and 1 are really the only candidates. But in order to get a 5 and a 1 to add up to 4, I would need a negative sign in here. So clearly it doesn't factor. So then I'm going to, all right, game plan 2, quadratic formula. Minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. 4 times 5 is going to be 20. 16 minus 20 is minus 4. So this is plus or minus the radical of minus 4 all over 2. Of course, this is going to be minus 4 plus or minus 2i all over 2. And so we get that our r is equal to minus 2 plus or minus I. So that is our r value. This immediately gives me the case that y is going to be c1 e to the minus 2t cosine t plus c2 e to the minus 2t sine t. So that's our general solution. So intro was correct as to the r value. However, she didn't really write down a general solution, so I don't know if she would have gotten that part. But I believe in you. I trust that you would have gotten this if you got that. So this is a complex solution, so we're in case 3. Now, of course, we want to plug in the initial condition, so I'm going to need to know what y prime is. Now, y prime, I'm going to need a product rule, right? So if I look at minus 2 c1 e to the minus 2t cosine t minus c1 e to the minus 2t sine t. That's the derivative of the first one by the product rule, plus, or in this case, it's going to be minus 2c2 e to the minus 2t sine t plus c2 e to the minus 2t cosine t. That's your derivative. Now y of 0 equals so this here is our second derivative, or our first derivative. Y of 0 equals 1, y prime of 0 equals 0. So this means I'm going to go to the original and plug in 0 everywhere I see t. And I would get the result 1. So if I plug in 0 everywhere I see t, remember cosine of 0 is 1, and then I have e to the 0 is 1, so that's just c1. Sine of 0 is actually 0. So that's already just equation 1. I can already tell the c value from that. If I go to there, to the y prime and plug in 0 for t's, I would get 0 on this side. Now, of course, everywhere I see cosine, that's going to become 1 because cosine of 0 is 1. Everywhere I see the sine, that's going to be 0. So the second and the third term I can ignore. I would get minus 2c1 for the first term, and then I would get plus c2 for the second term. But I already know that c1 is 1, so this is minus 2 times 1 plus c2. And so now I would get that my c2 is equal to 2. And so ultimately, my final solution is c1, which is 1. So it's just e to the minus 2 cosine t plus 2e to the minus 2 sine t. And that's our solution. Okay, so that's what this problem would look like. So this quadratic, should notice that it can't factor because you won't be able to get plus signs everywhere. If we had a minus sign like here, we could get it to work out, but we didn't. So jump to the quadratic formula. We got a complex root. That leads me to this version of the general solution. Differentiate it. Notice that we have to apply product rule because we have an exponential times a cosine and an exponential times a sine. So it breaks out in this. However, plugging in zeros, sine of 0 is 0, cosine of 0 is 1. So the trig functions immediately go away, as well as e to the 0 is 1. So the exponentials automatically go away. And we get some equations with c's only. Solve those equations simultaneously. The first one is actually pretty easy. It gave us the value of c1 right off the bat. And so ultimately now, that is our solution. I'm not sure why you're thinking of what you're putting for R. R is this. Right? So once you realize that what your R looks like, you think about this. You just look at what case you're in. You're in case 3. Now, once you're in case 3, your general solution is going to look like, that. So you're going to take the real part, put in the power of the exponential. You put the imaginary part in the cosine angle and the sine angle. Right? So for here, I know the general solution in this scenario is going to be c1 e to the at cosine bt plus c2 e to the at sine bt. And from here, I know that my a is minus 2 and my b is 1. So I just plug those guys into this general form, and that gives me this. The y prime of 0. In the y prime of 0, you don't need to plug in an r. You need to plug in a t. Right, the 0 here is the t, and this here is the corresponding y. The r doesn't even come into play. R came into play to figure out that this was the form that you had in the first place. But once you have that form, you forget about the r. You're plugging in the t's and the y's. For y prime of t, I just differentiated the y, right? This is y right here, differentiated. That gives you y prime. Right? Is it something between these two steps that's confusing you? Yeah, so I differentiate this. Of course, I need the product rule. Then I have to plug in zeros everywhere I see t's, and then plug in for the y prime, I would plug in 0. E to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, sine of 0 is 0, cosine of 0 is 1. All the exponentials raised to the power 0 goes to 1. So the second and the third term die because they have sine t attached to them. And the other parts, the C1 and the C2, their coefficients go off to 1. And so I get this equation. Okay, so that is that. I think that's all the examples I had for this section. So now we know how to solve second order linear differential equations with constant coefficients. Of course, you realize, hopefully by now, that memorizing what's in this table is going to be important for knowing how to actually solve them. You have to have these forms memorized in your head so that you know whenever I get an answer, if there are 2 real roots, I'm in case 1, the answer looks like this. If I have 1 repeated root, then I'm in case 2, the answer looks like this. If I have complex roots, then the answer is going to look like this. We're going to get sines and cosines popping up. And there we go. Now, the next thing I wanted to talk about was actually just some information about the solutions. But I'm not sure, can we actually go through all of this in the remaining time? Thinking, make an executive decision. Versus the next section is a little bit shorter. But then again, it's probably too short. Okay, so technically, again, we're going to go slightly out of order. I'm going to cover this before going to that, even though technically it would be better if you actually knew about this stuff going in. But I don't want to actually start this and stop halfway because it's going to be nicer to flow if you just see it all in one shot. So I might save this for the next class. Let's do this. Let's do in 3.4. So you're still going to have to take a lot of things on faith at this point. But in 3.4, I'm going to introduce a concept called reduction of order to you guys. And it is going to justify why the solution in case 2 looks like this. How do you know that when you have a repeated root, that the second part of the solution is just t times that guy, right? So that's what we're going to look at. Next class, I'm, Roberto's like, no, we can't. No, a lot of the things in this section, I'm going to actually talk you through. There's not many places for you guys to give input. So it's going to go by relatively quickly, but it's going to be a rush if I force myself to do it in like 25 minutes. As for quizzes, no, so next week should be your test. So I'm not going to give you a quiz next week because you're already having a test next week. I already reset the dates on the web work homework. So now let's actually do reduction of order. And again, this is kind of going out of order because at this point, you don't know why the solutions have to look the way they do or not, but let's just take it on faith that the solutions is going to be that. So what I would like you to take away from this is that whenever you have an equation like this, and you're in one of these cases, then this guy here, this answer here, represents all possible solutions that could actually ever exist. So even though we started this whole process with a guess, it turns out that that guess ends up being comprehensive. There is no other possible solution out there, this general solution will cover everything. And if you can come up with any other function, it will be possible to express that function in this form. So no matter what answer you can come up with for a second order linear differential equation, you can express it in one of these forms. And you can do it a little bit more generally as well, which is what the next section I was going to talk about. But it's always going to look like C1 times some function plus C2 times some other function. C1 y1 plus C2 y2. The y1 and the y2 have to have a certain relationship to each other. They have to solve the differential equation, and they have to be what we call linearly independent. Once you find two such functions, it does not matter how you find them. Even if you just blindly guessed it, it does not matter. The existence and uniqueness theorem is going to back you up. That's like your big brother that's going to get you in the club, right? You just make this guess, and it's all going to work out. These general forms that I just gave you represent all possible kinds of solutions that could exist. Any other solution that someone comes up with will either be exactly these guys, or I'll be able to algebraically simplify it to one of these guys, right? So that was something I was going to discuss in the next section. But let me just mention that to you, and we'll just take that for granted for now. And I will show you guys why did case 2 work out this way, right? But it's nice for me to use case 2 as a case study, but the method that I'll be doing, reduction of order, actually works a little bit more generally. So it's worth me showing you where case 2 comes from, because in showing you that, I'm actually showing you another technique that can be very useful. So here's basically how reduction of order works. Let's say, and I'm going to say this specifically to second order linear differential equations, but it can work a little bit more generally. It can apply to third orders and so on and so forth, but we're going to apply it to second orders, okay? So suppose we have an ODE for which we know one solution, okay? So this is like before, when we set up the characteristic equation, we only got one R value. So we know that e to the RT, that one function, is a solution. How do you find a second solution? Because it turns out, which is what I would have explained in this section, it turns out that the existence and uniqueness theorem tells us that you should be able to find two fundamentally different kinds of solutions. So if you only have that one e to the RT, there has to be someone else. How do you go about finding that other person? There is a technique called reduction of order that a lot of the times will work out and help you to find that other person. It works out for second order linear differential equations specifically. Here's how you think of it. You're going to guess that the second solution is just some function times the first. You don't want it to be a constant times the first. It cannot be a constant. It has to be some variable function times the first. And again, what I would have explained in the last section would tell you why that has to be true, but we'll just put that off for the next class. So if I know one solution, call it y1 of t, I want to find a second solution, y2. I am going to guess that this function has the form some function times y1, which we'll call v of t times y1. Then what I'm going to do is I'm going to plug that expression into the differential equation, and I'm going to get a second function, a second solution from that scenario. It turns out that in case 2 from what we just talked about earlier, the function v of t is going to end up just being t. This will always happen for a second order linear differential equation with constant coefficients that has a repeated root. In fact, I'm going to prove this to you. I'm going to show you that if I have a second order linear differential equation with constant coefficients, and it has a characteristic equation that gives you a repeated root, then I know that the second solution is going to be t times the first solution. Here's how we'd know. Well, to get a repeated root, that means the characteristic equation would reduce to something like this, r minus r1 all squared, where the r1 is the solution. We saw this happen in this example here. Here, we saw this happen in this example here, right? When I set up my characteristic equation, it ended up being a complete square, so there was only one answer, right? So that's what's happening here. if I get from a quadratic only one answer, it means the quadratic has to reduce to something that looks like that. Now, if I expand that, that means the original quadratic had to look like that. Now, if I backpedal and to look at what the original ODE must have looked like, well, the coefficient here would be the coefficient of the y prime. This guy here would be the coefficient of the y. And the 1 would be the coefficient of the y double prime. The standard form of the second order linear differential equation with constant coefficients that I'm looking at must have this form. So here I'm just backtracking. Assuming that I only have one solution to the quadratic, the original differential equation must have a standard form that looks like that. Now, again, I know the first solution is going to be y1 equals e to the r1 of t. So by the reduction of order, I'm going to guess that the second solution looks like this, v of t times y1. In other words, it looks like v times e to the r1t. What can I derive from that? Well, if my y2 is v times e to the r1 of t, then that means that my y2 prime is going to be v prime e to the r1t plus, and let me use r here just so it's easier to write down. So it's really r1, but let me use r because I can't be bothered writing r1 the whole time. By the product rule, differentiate the v, leave the e to the rt, plus leave the v, differentiate the e to the rt. So that would give me v prime plus rv times e to the rt. This also means that if I take y2 double prime, I'm going to differentiate this by the product rule again. So differentiate the first part, leave the second part, plus leave the first part, differentiate the second part. This means that this is going to be v double prime plus r plus 1 v prime plus r, this is actually r squared. So here it's rv prime plus an rv prime, so it's 2rv prime plus r squared v, all of that times e to the rt. Now plug into the ODE. This means, what ODE are we plugging it into? Well, the ODE that I know it had to look like. So I'm going to plug it into this ODE right here. Right, so I'm going to plug into this ODE. Now, if I plug it into that guy, what's it going to look like? Well, my y double prime is going to be this whole thing right here. So that's going to mean that v double prime plus 2rv prime plus r squared v e to the rt minus 2r times the y prime. This means v prime plus rv e to the rt plus r squared times the y, which in this case is v e to the rt equals 0, right? Now I'm being very general here. This is representing any possible second order linear differential equation that looks like this. Now, notice here that I can divide both sides by e to the rt because it's non-zero. I can then start combining terms here. So here I would have a v double prime plus 2rv prime plus r squared v minus 2rv prime minus 2r squared v plus r squared v equals 0. Now what's going to happen? I have 2rv prime minus 2rv prime. I have minus 2r squared v, but then I have a plus r squared v and a plus r squared v. So all of those guys actually die. This reduces to v prime equals 0. Now, this is why it's called reduction of order, because technically how we think about this is that we do a substitution, change it to a first order. In this case, you don't need to, but you would change it to a first order by setting u equals v prime. So hence is why we call it reduction of order. Now, in this case, it's not completely necessary because you can just see right off the bat, you're just going to integrate twice. But in general, you're going to get to a stage here where a lot of these guys are going to cancel out. This will bring you into the situation that we had in section 2.9, where you're only going to have a y double prime and potentially a y prime. They're going to be one derivative away from each other. So by doing this substitution, you can reduce it to a first order, right? You will get case, I forgot what we call this in the miscellaneous ODE, case 1. You will get case 1 from the 2.9 section in general. So here we can actually just integrate twice. So here my v prime is going to be some constant. Call it C1 if you want, or just some constant. And also my v is now going to be some constant times t plus another constant. So here I just solve for v. So this means that my y2 is going to be v times y1. This means it's going to be ct plus d times e to the rt. Now, if you actually, let's actually move these guys out of the way. Right? So here your y2 would look like c t e to the rt plus d e to the rt. You'll notice that this part here is redundant, right? Because I already have a c1 e to the rt in my general solution. And so what you'll notice is that this is your second solution. T e to the rt. So now you realize that whenever you're in this scenario and you have a repeated root, you are going to have c1 e to the rt plus c2 t e to the rt as the general solution. And that is what we would end up with. And that's how that's how we actually figured out this thing in the table. So I just told you this right off the bat, but why that's true is this reason right here, reduction of order. So that's where that second case comes from. So yeah, wow. It always, by reduction of order, what often happens is you cancel out a bunch of terms. It leaves you with a situation that you would have in 2.9, which you can just reduce the order and solve it. Once you solve it, you can figure out the second solution. And this is where the T e to the RT part comes from, right? So this is where it comes from. So this is what implies, this implies that the general solution is going to be y equals c1 e to the rt plus c2 t e to the rt. Because if you have two individual solutions, e to the rt and t e to the rt, then a linear combination of them is a solution. A linear combination just means you multiply each by a different constant and add them together, potentially different constant. And again, why that would be how you look at the solution is something that I would have mentioned in the previous section. But for now, just take my word for it. That's what you string these two solutions together in this way. That is going to give you the general solution. And in fact, This represents all possible kinds of solutions that could ever exist. So you might be worried that, hey, we just randomly guessed that e to the RT was going to be an answer, and then we just happened to use this technique to get this other guy. How do I know that the answer couldn't be different? How do I know that there isn't some other answer out there? Well, we know by the existence and uniqueness theorem. The answer here is unique. And once I find two linearly independent solutions for a second order linear differential equation, that a linear combination of those two guys represents all possible solutions, meaning any other solution you can come up with, I can express in this form. And if you come up with something that cannot be expressed in this form, then it's actually not an answer. That we'll actually talk about next week. So let's actually look at some examples here. Consider the following ODEs. One solution is given, so I'm telling you one solution. Find a second via reduction of order. Right? So this of course you could find both solutions by using what I told you previously, but here we're going to use reduction of order specifically, just for you to see how it would work out with actual numbers. Okay, so let's say I have this. Now we know how to solve this. In fact, this is one of the previous examples that we had, I believe. Maybe, doesn't matter. Let's actually do it. So here, let's just show you how a reduction of order is going to work. For some reason, you're in a scenario where there's a differential equation. It's very important for you to solve, or else, you know, if you don't do this, millions of people will die, right? There's a guy, there's an alien, he's gonna blow up the planet unless you can find both solutions to this differential equation. And so far you only know one of them. And it's like, will our heroes find the second solution? Suppose you know a first solution, how can you get to a second one? Reduction of order is going to be one possible way. So here I'm going to assume my second solution looks like v times the first solution. In other words, v times e to the t. This means that y2 prime is going to be v prime e to the t plus v e to the t. Right? So that's going to give me like v prime plus v e to the t. Then I'm going to find y2 double prime. That's going to be the derivative of the first times the second plus the second times the derivative of the times the first times the derivative of the second. I can combine these. This is going to be v double prime plus 2v prime plus v times e to the t. Plug in to the original ODE. So I'm going to have y double prime minus 2y prime. So it's going to be this guy minus 2 times the derivative. So that's going to be v prime plus v plus the original y, which I'm assuming is just v e to the t. That should be 0. I can divide both sides by e to the t. And what are we going to have? Well, now I'm going to have v double prime plus 2v prime plus v minus 2v prime minus 2v plus v equals 0. Now I start to cancel. 2v prime minus 2v prime, that goes away. V plus v is 2v minus 2v, that goes away. I get v equals 0, which is pretty obvious here. That, integrate again, we get that. Then my y2 is just going to be v times e to the t, which is going to be ct plus d e to the t. This is going to be ct e to the t plus d e to the t. And so the second solution is that one. Now, so y2 equals te to the t is our second solution. Now, because this is always going to work out this way, that's why I just skipped ahead and I told you guys in the table, like, don't bother going through a whole process to figure out the second guy. The second guy is always going to look like a t times the first guy, if you're in the scenario of a second order linear differential equation with constant coefficients, which in this case we are. This is a second order linear differential equation with constant coefficients. If I know one guy that doesn't have a t multiplying, just multiplying by t, I get the other guy. Now, it's not always as obvious when you don't have constant coefficients. So if you look at this example over here. Okay, so here, notice that we don't have constant coefficients. I have a t squared y double prime minus a 2ty prime minus 10y. My first solution is t to the fifth. Find a second solution, and you can actually check. Find the second derivative of t to the fifth, find the first derivative of t to the fifth, and plug this into the differential equation. You'll realize that you'll get 0. So we're actually going to look at how to solve this guy from scratch in chapter 5, but for now, here's the differential equation, here's one solution, find a second solution. I'm going to assume the second solution is some function times the first solution. That is some function times t to the fifth. This means my derivative is going to be v prime t to the fifth plus 5v t to the fourth. And this also means that my double prime is going to be v double prime t to the fifth plus 5v prime t to the fourth plus 5v prime t to the fourth plus 20v t cubed. The second one I can clean up a little bit. I can combine the v prime t to the fourths. So this is v double prime t to the fifth plus 10v prime t to the fourth plus 20v t cubed. Now I'm going to plug into the original ODE. So this says t squared times y double prime. So I'm going to have t squared times this whole guy right here. Then I'm going to have minus 2t times y prime. It's going to be minus 2t times y prime, which is this guy right here. Then I'm going to have minus 10 times y, which I assumed is vt to the fifth. And all of that should equal to 0. So now let's actually combine terms and see what this looks like. So this looks like v double prime t to the seventh plus 10v prime t to the sixth plus 20v t to the fifth minus 2v prime t to the sixth minus 10v t to the fifth minus 10v t to the fifth equals 0. What's going to happen? Well, here I have minus 10v t to the fifth minus 10v t to the fifth and a plus 20v t to the fifth. So all those guys die. Here I have a 10v prime t to the sixth minus 2v prime t to the sixth. So that just leaves me with 8v prime t to the sixth. Then I have the v double prime t to the 7. Notice that my t is positive, it's not 0, so I can divide through by t to the 6. Now here, I can just set u equals v prime, and we end up with the equation u prime times t plus 8u equals 0. Hashtag reduction of order. We went to a first order differential equation. So I can now start solving the second order differential equation by considering this first order differential equation. Now for this one happens to be, it's linear, but more easily than that, it's actually separable. So this, I would say, I would have here t times du dt is equal to minus 8u, and I would divide both sides by u. And then here I would have minus 1 over t dt, minus 8 over t dt. At this point, I can integrate both sides. So this is going to give me ln of u equals minus 8 ln of t plus c, which I can write as ln of some constant times t to the minus 8. So this means that my u is equal to t to the minus 8, or some constant times t to the minus 8. But my u is v prime. Which means I can solve for v by integrating that, add 1 to the power, divide by the new power, but this is just going to be some other constant, plus some other constant. So this means my second solution is v times the first solution, which is t to the 5th, which is going to now be ct to the minus 7 plus d times t to the 5th. This is going to be ct to the minus 2 plus dt to the 5th. This guy here, redundant. We have already accounted for him, which means that this guy here is our second solution. Right? And by the way, BTW, this means the general solution to that ODE is y equals c1 t to the 5th plus c2 t to the minus 2. And there you have it. That is reduction of order. Notice that it can work even in the non-constant coefficients case. However, in the constant coefficients case, you pretty much always reduce to something like v double prime equals 0. So it just makes it very trivial. You just know you're going to multiply by a t to get the other guy. Nothing much to do there. And for these ones, now at this point, you would have gone the entire weekend before seeing this section again. So at this point, I expected you guys to have forgotten a little bit of what we spoke about today. But right now, you can just find the general solution of the following. You don't need to use reduction of order. Just apply the previously described solution, which is what I gave you in the table. And hopefully now you'll have a new appreciation for the pattern, why there was a t attached to one of them. So now here, I can just say, well, this is r squared plus 10r plus 25 equals 0. You can notice that this is actually r plus 5 all squared equals 0. So this tells us that r equals -5. So in fact, here, what you'll notice, we know that one solution is y1 equals e to the -5t by reduction of order. We know the second one. We now know the second, and there must be 2 for a second order, is y2 equals t e to the -5t. And so this leads us to the final conclusion that the general solution is going to be c1 e to the -5t plus c2 t e to the -5t. And that's why I gave you that summary in that table. This is always going to work out. Why? Because if I had used reduction of order, I would just get a t attached here, because I would have gotten my v double prime equals 0, which would end up making me multiply by something like ct plus d to the original. And this is going to be the second solution. Similarly here, just one other example, and then we wrap this up. I start this. I would jump into 4r squared minus 12r plus 9. This guy, I believe, factors into 2r minus 3. You can check. 2r squared is 4r squared. Minus 3 squared is 9. This times this is minus 6r times 2 is minus 12r. So yes, that is the factors. And so my r is going to be 3/2, but that's only one solution. This means the general solution is c1 e to the 3t over 2 plus c2 t e to the 3t over 2. And this gives one solution, which is e to the 3t over 2. Reduction of order gives the other. Namely, te to the 3t over 2. But you can always now, from now on, you can just assume that that's going to happen in this scenario, and you just write down the general solution. And yes, I agree with the comment. It's very cool. So that's reduction of order, guys. As you can see, it does work a little bit more generally than with constant coefficients. Here's an example with a non-constant coefficients. We're actually going to, this type of equation here is called an Euler's differential equation. We're actually going to deal with that in chapter 5. But for now, hopefully you have some appreciation of why the solution had to look like that. You will have even more of an appreciation for that as of next class, where I'm going to go back. I'm going to talk about solutions to second order ODEs and even higher than second order ODEs, why the solutions have to behave the way that I'm telling you that they behave, and what are some characteristics of these solutions that we can take advantage of. So that's it for today's lesson. Yeah, I would have never made it through this today, but we got through 2 sections, so I'm happy for now. Your test is next week, Thursday, and as such, I'm not going to be giving you a quiz, because to give you a quiz and a test on 1 week, come on, what am I, a Nazi? All right, so now that's what we're going to have. And in fact, because it's the summer, it's going to be tight. You guys knew this coming into this. And so your test is going to cover everything we cover up to the day before, which is on Wednesday. So this is something I'm thinking about, and I'll probably just reach out to you guys to make sure, maybe do like some sort of poll. But I was thinking instead to just have a regular class on Thursday, and I just have you guys do your test on maybe like Friday during your own time. But I would have to find a window that I don't want to make too big, that everyone would be able to take the test. Otherwise, I'll just give you the test on Thursday. So if you guys think, if pretty much everyone would be available at some point on Friday, maybe roughly around regular class time, I guess would be the most convenient, you guys can let me know. Is there anyone here who would not be able to do it on Friday? That way you can get another day to study. Is there anyone here that no time on Fridays? It's possible. You have work in the evening? If I do it around regular class time on Friday, is there anyone who can't do it? So let's say I was to schedule a test for sometime between 9 a.m. and 3 p.m. Would everyone be able to fit sometime in that window? Is there anyone who can't fit that window? So if the answer is yes, that's great. I'm interested in the no's though. So if you think that time is impossible. Hi, Zkong, can you hear me now?
Yes.
Okay, so I'm just saying, because there's going to be a rush, because everything that's covered up to Wednesday would be on the test on Thursday, I'm thinking I can give you guys, just have you guys do the test during your own time on Friday. And so I just want to make sure that everyone can make a time.
All
So
right.
is around regular class time on Friday doable for everybody?
Fine.
Okay, so we can actually do that. And I'll send out an email confirmation about this, and everyone will have another chance to tell me. But I think that's a little bit of a cushion I can give you. There's not much cushion I can give you in the summer, but we can do that. So we can have a regular class on next week, Thursday, and then Friday during regular class time, even though there is no class, you take the test on your own time. That'll give you another 24 to 48 hours break to study. But the test will cover everything up to what we do on Wednesday. All right, that is that. Let's end things right there. Hopefully you guys enjoyed that class. We will be filling in a lot of the gaps in the knowledge that we have next class. Rebecca, send me an email about that because I need to check. But as of now, the test will be on whatever we cover up to Wednesday's class, and I will give that test on Friday. So you'll have roughly 2 days to study, and yeah, that's it. For now, we are going to end there. Yeah, Thursday I'll just be a regular class, not a review class. It's the summer. We can't afford any review classes. So it'll be a regular class. I'll just continue, but you can essentially just ignore everything I do on Thursday in regards to the test that will be on Friday. With that being said, we'll stop there. Hopefully you guys have a great rest of your day, and I will see you guys in the next one. Ciao.